Welcome to Lecture 1 of Week 3 for Math 320. Our goal today is to give a definition of the concepts of supremum and infimum. Well, actually, you've already seen them hiding in last week's lectures, but this week I'm actually going to come out and call them by their names. Manipulation of the supremum and infimum is one of the most useful tools for building up our toolbox for dealing with the real numbers. So we will be spending a lot of time this week working on how to reason with suprema and infima. Do make sure to do your exercises. Yes, many of them look absurdly simple, but you should take the time to try to write out every single step. It will pay off later this course when we deal with more complicated arguments if you have some fluency handling proofs using these two concepts. Let's define supremum and infimum. It turns out they're just fancy words with Latin roots that mean the least upper bound and the greatest lower bound of a set when they exist. The supremum of S, written sup S, is the least upper bound. The infimum of S, written inf S, is the greatest lower bound. One of the consequences of the completeness property of the real numbers is that whenever S is a bounded, non-empty set, the quantities sup of S and inf of S exist. Since these words have Latin origins, they have funny plurals. The plural of supremum is suprema. The plural of infimum is infima. Let us remind ourselves of the least upper bound and the greatest lower bound properties again. The least upper bound property: if S is a non-empty set of real numbers that is bounded above, then sup S exists. The greatest lower bound property: if S is a non-empty set of real numbers that is bounded below, then inf S exists. Now let's return to the definition again to make sure we really understand what it says. Specifically, I want to expand on the phrase least upper bound and really get into the nitty-gritty. So if S is a set of real numbers, then sup S, if it exists, is the unique number x0 that satisfies two properties. First, it is an upper bound of the set S. This means that if S is an element in big S, S must be less than or equal to x0. Second, it is the smallest possible upper bound. Another way to say this is that no smaller number can be an upper bound. Mathematically, this can be expressed as the condition. Whenever t is a number smaller than x0, then we can find another element S in S such that t is less than S. Remember that being an upper bound means that a number is at least as big as any number in the set S. So, to negate that, if we can find one or more numbers in the set S that is bigger than t, this is the same as saying that t is not an upper bound of S. Please pause the video for a few seconds now and see if you can formulate an analogous definition for the infimum, remembering that the condition is that of the greatest lower bound. It is perhaps illustrative to think about how we could put this definition to use in practice. So, given a set S and a number x0, how do we prove that x0 is the sup of S? Let's think back to the definition. There are two conditions that need to be met for x0 to be the supremum. First, we need to check that x0 is at least as big as any member of the set S. For this, you will certainly use the definition of the set S. Second, you need to check that any number smaller than x0 cannot be an upper bound for S. This means you need to find for any t that is less than x0 an element S in S that is bigger than t. In addition to the definition of S, frequently you will have to rely on some version of the Archimedean property to make this work. Let's consider a simple example to illustrate the principle. We can take the set S to be the set of numbers looking like pi minus 1 over n for some natural number n. I want to show that the supremum of S is exactly pi. We have two parts of the proof. First, we need to prove that pi is an upper bound. To do so, we need to show that every element of S is no bigger than pi. So first, we take S to be an element of S. Using the definition of the set S, we know the element S must be pi minus 1 over n for some natural number n. And since 1 over n is positive for any natural number n, we have that S is no more than pi. This shows that pi is an upper bound for the set S. Notice that the argument would have worked if we considered any upper bound of S. For example, 4. If you swap out the letter pi for the number 4 in steps 2 and 3, you get a proof of 4 being an upper bound of S, provided you remember that pi is no more than 4. So the first part works for all upper bounds. That is because it is designed to do so. To make sure pi is the least upper bound, and not just any upper bound, we need to check that there cannot be a smaller upper bound. So we need to start with an arbitrary t that is less than pi. Our goal, of course, is to show that t cannot be an upper bound. So eventually, we have to arrive at showing that there is an element in the set S that is bigger than t. That t is less than pi means pi minus t is positive. From the positivity, we can now make use of the Archimedean property, one of its formulations in terms of corollary 21 on the reusable usable formula sheet, which is also exercise 2.16 from the exercise sheet from last week, is that there exists a natural number n such that 1 over n is no more than pi minus t. So, if we rearrange this consequence of the Archimedean property, we find that for that chosen n, t is smaller than pi minus 1 over n. This number pi minus 1 over n happens to be an element of S by definition, and hence we have exhibited an element in S, namely pi minus 1 over n, for the n that is determined abstractly from the Archimedean property, that is greater than t. And this concludes our proof. And let's ask the opposite question. How would we prove a number is not the supremum of a set? Whereas checking a number is a supremum requires checking two things, making sure they are both true, checking a number is not a supremum, just requires one of the two things turn out false. In particular, if you can show either that x0 is not an upper bound of the set S, or that x0 is an upper bound, but there is an even smaller upper bound, then you will have succeeded in showing that x0 is not the supremum. Let's give a couple examples. Our first example is a lot like our last one, except now we're looking at the square root of 2 instead of pi. So S is the set of all numbers that look like square root of 2 minus 1 over n, where n ranges over the natural numbers. We will show that x0 equals 1 is not a supremum. In this particular case, The reason that 1 is not a supremum of S is due to it not being an upper bound. To demonstrate that, we will need to exhibit an element of S that is bigger than 1. At the end of the proof, we will see that the square root of 2 minus 1/3 is bigger than 1. To prove this, we start by considering 1/3 plus 1 equals 4/3. Since 4/3 is positive, and squared equals 16/9, which is less than 2, we conclude that 4/3 is less than square root of 2. And hence we can rearrange to find 1 is less than square root of 2 minus 1/3, which, being in S, is an element of S that is bigger than 1. This shows that 1 cannot be an upper bound of S. Contrast this with the proof in the previous example. To show that x0 is an upper bound, we need to show that for every element of S of the set S, S is less than x0. To show that x0 here is not an upper bound, it suffices to show that there is one element S of the set S that is bigger than x0. Again, we see that the negation of a for all statement is a there exists statement. The last example shows you what to do when x0 fails to be a supremum due to it not being an upper bound. There is another possibility, and that is x0 can be an upper bound, but just not the smallest one. In the next example, we will take the same set S, but we will try to show that x0 equals 2 is not the supremum of S. In this case, we will show that while 2 is indeed an upper bound, it is not the smallest such. We will claim that 3/2, which is less than 2, is an upper bound of S. Having found a smaller upper bound, we can then conclude that 2 cannot be the least upper bound. To show that 3/2 is an upper bound, this is again an exercise in inequalities. We need to show that 3/2 is bigger than square root of 2 minus 1 over n for any n. So, to do this, we will first study the number 3/2 plus 1 over n, which is equal to 3n plus 2 over 2n. This is a positive quantity, and squaring it, we find its square is at least 9/4, which is bigger than 2. This shows that 3/2 plus 1 over n is bigger than root 2. Or that 3/2 is bigger than root 2 minus 1 over n. Since every element in S is of the form root 2 minus 1 over n, and n has been arbitrary but natural, throughout this proof, we see that every element in S is less than 3 over 2, showing that 3 over 2 is another upper bound. This shows that 2 cannot be the least upper bound. Again, we can compare this to the proof of x0 being a supremum. To prove that x0 is a supremum, we need to show that every t smaller than x, there exists one element in S that is bigger than t. To prove that x0 is not a supremum, we need to show that there exists t smaller than x such that every element in S t. So again, we see how the negation swaps the quantifiers. Okay, that's it for today. But in this final slide, I show you how to type up sup and inf in LaTeX. See you next time.